Okay, so hello everyone and welcome to the day 4, lecture number 4 of our workshop. I hope you enjoy the workshop so far, and Krzysztof, if you are ready, we can start.
Okay, so once again, hello everyone. Today we have quite a long agenda, so I suppose the lecture will be longer than yesterday's. I suspect about 1.5 hours. But yeah, today we will cover some of the basic quantum protocols, such as superdense coding and quantum teleportation protocol. And we'll also cover the basics of those protocols, which is entanglement. But first, I want to talk about the 2-qubit gates, which are two Hadamard gates and the control NOT gate. So to begin with, I'd like you to think about what it means and what is the matrix representation of both qubits of applying Hadamard gate to 2 qubits. So you now may be familiar with this notation of wires and the gates as the blocks. This is a very common way to represent gates in Qiskit. So actually, let's calculate the state if both qubits are in 0 state. Let's see what is the resulting state after applying to Hadamard. So as you may recall from yesterday's lectures, that Hadamard transforms the state 0 to state 1 over square root of 2, 0 plus 1 over square root of 2, 1. And the same goes for the second qubit. Now let's try to represent all of those, this tensor product as in the form of those cats with two indices. So actually you can think of, this is for example the first qubit, and this is the 0th qubit. So actually you can think of as this tensor product that you put the zeros inside those two cats, but the order of this operation matters. So after the multiplying of this tensor product, we will get in the vector notation something like 1 over 2, because now 1 over the scalars we have to multiply the scalars. So this is 0, 0 plus 1 over 2, 0, 1 plus 1 over 2, 1, 0, and 1 over 2, 1, 1. Now let's think of how to write a 2 Hadamards as in the vector representation. So the Hadamards, as you may recall, are 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2. And we'll calculate the tensor product, the matrix, the same matrix. I do this so you could see how the tensor product works, and therefore you'll be familiar with it once it appears on more sophisticated algorithms, and you won't be afraid to do so. So in order to calculate the tensor product, we have to put this matrix before each and every element of the second matrix. Therefore, the resultant matrix will be not 2 by 2, those are 2 by 2 matrix, but a 4 by 4 matrix. So now let's try to think of something like, I will write 1 over square root of 2 for easier calculations. So 1, 1, 1 minus 1 times 1 over, actually no, this may be more confusing. I'll stick with the notation I have so far. So 1 over square root of 2, 1 over square root of 2. This will be a lot of writing, but I hope you will get the idea. So this is the first matrix in front of the first element times 1 over square root of 2. And now we will copy the same matrix 3 times. It's very convenient to use the graphic tools. Okay, so here shall be also 1 over square root of 2. I may make this line bigger. Here will be also 1 over square root of 2. This is times, not minus. And this is times minus 1 over square root of 2. And the resultant matrix is, maybe now I can get rid of all of these square root of 2's and write 1 over 2 in front of the whole matrix. And now we have 1, 1, 1, minus 1. And we can divide this into 4 parts. We also have 1, 1, 1, minus 1, 1, 1, 1, minus 1, and minus 1, 1, 1, 1, because of the minus in front of here. So yeah, this was a quick introduction to the tensor product and how you may think of it and how to calculate it. Now let's talk about the CNOT gate. As we talked about before, the matrix representation of this gate is 1, 1, 0, 0, 1, 1. And here are all zeros. If I write this big 0, this means that all the entries in this 4x4 matrix are zeros, and it's just for faster writing. So we talked about it earlier that the CNOT gate flips the second qubit only if the value of the control qubit is 1. So in this case, nothing happens because the first qubit is the control qubit and the second qubit is the target qubit. So this is control. And this is target. And this gate only works when the the control qubit is 1. So now actually if the control qubit is 1, the resultant state will be 1, 1, and this is therefore now changed. And in this case, the resultant state would be 1, 0. Okay, I think we have covered the basics of 2-qubit gates. Now let me talk about the phase kickback phenomenon. So imagine a circuit like this. I'm going to paste it here. Imagine a circuit like this. And we'll calculate the state of this circuit, of 2 qubits in the circuit, at each and every step of this calculation. And at the end, hopefully we will see some intriguing phenomena that happens. So right now, you may suspect that the qubit 1 is the control qubit and the qubit 0 is a target qubit. So the state of you may expect that the state of the second qubit, the 0 qubit, will be changed based on the first qubit. And we will see what actually happens. So we begin with the state 0, tensor product with 0. And now we will flip a little bit the notation. And actually, this is the 0th qubit, and this is the first qubit. We'll write it in this notation. So after applying the Hadamard gate, the X operator to the first qubit, so we'll use the cascade notation, we have 0, tensor product 1. Then we applied Hadamard gates to both qubits. Therefore, we obtain 1 over square root of 2, 0, plus 1 over square root of 2, 1. And this comes from this qubit here. And tensor product of the first qubit, not the 0th qubit, but the first qubit, will be 1 over square root of 2, 0, but now minus 1 over square root of 2, 1. And this minus comes because the Hadamard gate applied to the 1 state give us the state described here. So we will mark it as belonging to this state. So after applying the Hadamard gate, we have those states. Now, let me rewrite this a little bit in such a form that we will split this tensor product into 2 different sums, because it will be easier for us to then apply a CNOT gate. So once again, now I write the state of the, this is the 0 qubit. So let's say Q0. And now I will rewrite the state of the first qubit. So this will be Q1. And as again, minus in front of the 1. A lot of calculations today, so we'll have to be quite patient. Again, rewriting the state of the first qubit. 1 here, but I also forgot to bring 1 in front of the whole expression, so I will try to move it. And okay, so this is also the state of Q0, and this is the state of Q1, but rewritten in such a form that now it is easier to apply a control CNOT. Because now the 0th qubit, I'm sorry, the first qubit is the control qubit. So, okay, so now after the CNOT gate, we see that the 0 qubit does not change the state of this qubit, but the 1 state applies a NOT operator to both qubits. Therefore, we can see that after the CNOT, we have square root of 2, 0. So I will copy this and paste because this stays the same. Maybe I'll try to copy all of this. Okay, so after the CNOT, now the 1 changes the state of this qubit here. So this will now be 1 and 0. So let me again rewrite this and say that I'm sorry. Okay. Let's try to once again. Okay, paste it. So this is equal to, now we place the minus in front of the bracket and we change the order of those of those two states. So this is exactly equal to the expression below. I see the comment on the chat, something. Can you explain how to solve this circuit once again? You mean the circuit here, right? Okay, so I will finish the calculation and then explain it once again. So yeah, now let's try to go back to the form with two brackets. So let's try to combine those, and we will get 0 minus, because now we have minus 1 over square root of 2, 1 tensor product with exactly the same expression qubits. Sorry, this should be 1 here. Okay, and now we apply Hadamard gates to both qubits. And after the transformation, we get a state 1, 1. So once again, but what is important here is that here we started with states plus and minus, but after applying the control C naught, we end up with a state that's with a changed phase. So the phase changes from plus to minus after applying the C naught operator. And this phenomenon in quantum physics, in quantum computing, is called a phase kickback. And it refers to the fact that controlled operators have effect also on their control. So, okay, let me review the circuit once again and maybe try to change the screen a little bit. So once again, we have a qubit 0 and 1. We apply a NOT operator on the first qubit. We apply Hadamard gate to both qubits. The 0 qubit has the plus sign, so it has positive phase, let's call it. And the 1 qubit after the Hadamard has a negative phase. Now we rewrite our expression in this form. So therefore applying a C0 operator will be easier. The C0 operator is, so actually the 0th qubit is the control qubit and Q1 is the target qubit. So this state of this qubit is changed. So the zero state does nothing to our first qubit, and the 1 state changes after the C naught changes the state to 1 and 0. I can write it here. So this is X operator because of the 1 in front of the bracket. Then we rewrite, after the transformation, we write our expression again. We rewrite our expression so that the minus is transferred in front of the bracket. And then we rewrite our expression to the tensor product of two brackets. After the Hadamard, both states get transferred to 1, 1. So in this case, as I said, the phase kickback refers to the fact that we begin with a positive phase, but after applying the C naught, we end up with a negative phase. And you can see that actually the 0 qubit was the control qubit, and the first qubit was a target qubit. So you may think that the state of the target qubit should change, but you can see that actually the state of the zeroth qubit changed, right? The phase of the zeroth qubit changed. So even though it was a control qubit, it also was affecting during the computation of the CNOT. Okay. Can you please explain how we got -1 over square root of 2 after applying the CNOT gate? So after applying the CNOT gate, we only change the those coefficients stay the same, but the CNOT applies an X gate. So the 0 state changes to 1 and the 1 state changes to 0. And then we manipulate with the sign. So we take our sign in front of the bracket and then we write our expression. I got another result from Qiskit Composer as 1. As 0, 1. Because here we have some different gates. Identity, this is X1. But I think you missed here this is the same. Qiskit Composer. I don't know what is. It's quite strange. I don't know what happened here, to be honest, in this screenshot you gave here. Maybe I'll try to calculate after the lecture. Maybe the sequence of the qubits is different. It may be. Or it has only 2 counts. It also may be.
Excuse me, may I have a question? Do you use
Yes.
the Qiskit convention or the mathematical convention? Because I got lost a bit
Here?
in
Or
all this calculation that you've made.
what do you mean Qiskit convention? Do you mean
Because when we were talking about, for instance, here like x parenthesis 1, yes, over
Yes.
the arrow, you said that you use Qiskit convention, yes? That's what I remember.
X parenthesis 1?
At the beginning of the calculus, you know, when you have
Here?
been no, below.
Low?
This calculation at the bottom. I
Yes.
only say about this one, yes? And
Yes.
when you name
Right.
the beats and so what convention do you use?
So actually you can, well, here I label those 2 qubits, and this is the first qubit is Q0 and the second qubit is Q1. So actually this is the Qiskit convention. You may, I mean, I'm not exactly sure if it's a Qiskit convention or not. Here, I just assume that the first bit is the 0th bit and the second bit is the 1 bit, as you can see here. So you can read from the bottom from like this, right? This corresponds to those bits here.
Okay.
And this is also, this whole bracket is a state of Q0 and this is state of the Q1.
One more question. The target bit is the Q1 or Q0?
The target bit is Q1 in this example. Maybe the image here is a little bit broken, to be honest. Maybe it should be different. Because now I see there may be a mistake, but I'll try to correct it later if it is. Because now I spot the a mistake in this. The calculations are right, but maybe the image here is broken.
So you mean that the C naught should be the opposite side to the
Yeah, I think so. I think so.
So the plus should be in the Q1 line, yes? I mean, the plus on the graph, yeah?
Yes.
Yeah, okay.
Yes. Okay. Yeah, thank you for the comment here.
Thank you.
So now let's move on to the entanglement protocol. And we will start with the circuit right here. And we will try to analyze, also track the evolution of both states. So let's apply a Hadamard, but now I'm using a little bit different convention. So I place 2 bits in one cat, but you can also write it as which is equal to also 0 tensor 0. But let's apply a Hadamard gate, as in the example here. So after applying the Hadamard gate on the 0th qubit, and now you can see that here is written from up to bottom. So like this. And applying a Hadamard gate on the 0th qubit will give us 0. Sorry. Will give us the Hadamard gate on the first qubit will give us 1 over square root of 2, 0, plus 1 over square root of 2, 1, tensor, actually, no. Actually, I will write this in this form right here. 1 plus 1 over square root of 2. I'm sorry, here is 0. And here is now 1. Now let's try to apply a CNOT gate, where the first bit is the control and second is target. And after applying the CNOT gate, we will get the state 1 over square root of 2, 0, 0, because the state is not affected, plus 1 over square root of 2. And now the first qubit is the 0th qubit is 1. So it will stay 1 and change the bit of the second qubit, which is now 1, 1. And now you can see those 2 qubits are entangled. Why? Because if you measure the state of the first qubit, of one of the qubit, you will instantly know the value of the second qubit. Because if this is 0, then the another one must also be 0. And no matter how many tries you get, you will always get both 2 zeros, or only 2 ones with equal probability. So the probability of obtaining state 0, 0 is 1 over 2, which is this value squared. And again, also the probability of obtaining both qubits in state 1 is also 1 over 2. And this is very strange, and actually it puzzled Einstein for a very long time, because imagine you could separate both qubits at a distance many, many light years away. And measuring only one qubit will give you instantly the information about the second qubit. But Einstein knew that information can travel only at the speed of light and not faster. And that's why it was very spooky. He called it spooky action in a distance. But actually, those 2 states are inseparable. So what I mean by that is you measure a By measuring one qubit, you measure the whole quantum system, not only one qubit. And the whole quantum system happens to be in an entangled state. So it can only be both qubits in state 0 or both qubit in state 1 with equal probability. And the entanglement give us the foundation of two protocols, which is super dense coding and quantum teleportation. And we will start with super dense coding. So in this algorithm, suppose we have a quantum circuit like this. So first we entangle two qubits. Then here's Asias and Balvis. So two of those guys can separate each other. And now Asia encodes 2 bits of information, can encode 2 bits of information on her qubit. So if she wants to send a message to to Balvis, I'm sorry, AB, she can send 4 messages. 0, 0, 0, 1, 1, 0, and 0, 0. And in classical computing, she would have to send 2 bits of information, right? For Balvis to receive a message. 2 bits. But in quantum computing, in this case, she may only send her 1 qubit to Balvis, and then he would be able to measure correctly the state and get information, the message she wants to send, but only with 1 qubit, because the other one is kept. The other qubit he's keeping to himself. He doesn't need to send it. So let's also go step by step through this algorithm. We start with a 0, 0, and we know now that after the entanglement, we after those 2 gates, we end up with a state 1 over square root of 2, 0, 0, plus 1 over square root of 2, 1, 1. Yes, we already calculated this before. So now, depending on the information she wants to send, the Asias will apply either this, let's say this is Asias qubit, and this is Balvis qubit. So now let's try, I'm sorry, here we should be 1, 1 bits. Let's apply both gates. So she wants to send the information 1, 1. So she'll be applying gates Z and X to the first qubit. So after the first Z, the state of the qubit will become 1 over square root of 2, 0, 0, minus 1 over square root of 2, 1, 1. The minus comes from the fact that the Z changes the phase of the first qubit. Okay, so now let's apply the X operator to the first and the second qubit. So we have now 1 over square root of 2, 1, 0, plus minus 1 over square root of 2, 0, 1. Okay, and now we have another control knot from the controlled knot from the from here. So now ICS sends her qubit back, and we apply another controlled C knot. But here also the ICS ACS qubit, so the first qubit will be control, and the second will be will be the second qubit will be the target. So this is control. So in this case, we have 1. So the state will be transformed to 1, flipped to 1. So it's 1, 1. Minus 1 over square root of 2. Also 1, 0, 1. And now let's try to write it as a tensor product because the application of Hadamard gate will be easier. So in case of the tensor product, we'll have the qubit in state something like this one, minus 1 over square root of 2, 0. And 1, tensor 1. But we can also get rid of the minus sign in front and now write 1 over square root of 2, 0, and minus 1 over square root of 2, 1. Tensor product with state 1. Now, applying a Hadamard operator on the 0 qubit will give us here we apply Hadamard, will give us minus 0. And I'm sorry, this will give us minus 1. Minus 1, tensor product with 1, which is equal to minus 1, 1. Here we have a phase, but in fact, in the measurement, what we would measure are bits 1, 1. So after the, as we talked about yesterday, the global phase in the measurement gets lost. So what we're left with is the state 1, 1, and this is exactly the information the ICS wanted to send to Balvis, but she did it by sending only 1 qubit. So this demonstrate that possibly a quantum communication may be faster than classical one, but it requires completely different approach. So it poses the question how to send a qubit. Maybe a photon be a qubit. In fact, it can act as a qubit, but it is a very quite recent area of research, and this is still something under development. Let me know, and you can verify also the same algorithm in case of different bits that Alice wants to, that ICS wants to send to Balvis. Now let me move on to quantum teleportation protocol. And maybe do you have any questions to this super dense coding so far? Can we use entangled qubits for quantum communication? Yes, and in fact, entangled qubit, a pair of entangled qubit, there is a quantum communication protocols, for example, a BB8 or a quantum teleportation protocol that was discovered by Arthur Eckert, a Polish scientist. And they showed that it is possible for a perfectly secure communication. So let's try now to think that we have an eavesdropper here that wants to take the message of ICS. But if the eavesdropper measures the qubit, it has only access to 1 bit of information because the other bit is stored by Balvis. But also, you can create a protocol in which the key that it's quite a different protocol rather than here, but you are able to verify if someone is listening to your message or not. So using quantum communication, you are able to detect if someone is listening to your message. And if they are listening, you can just stop and abort the protocol and stop sending the message. But if you are sure that no one is listening to your message, you can then measure your qubits and receive the message from another person. Are there any more questions regarding this? If not, I will move on to quantum teleportation. And the quantum teleportation call is I like it very much because it's quite an elegant algorithm. And in classical computing, it's very easy to copy and store another bits. But in quantum computing, it is not possible to create a copy of the bit. But you can transfer a quantum state of one bit to another bit. And this is done by using a quantum communication protocol. So let's now assume that we want to transfer the state of the 0 qubit to the state of the second qubit. And you may think of it as, for example, Alice and Bob. They prepare the entangled state of 2 qubits, so qubit 1 and qubit 2. Then Bob's move far away, so we have Alice and Bob. And Alice has the qubit 1, and Bob has the qubit, goes away with qubit 2. And now we want to send our qubit 0 that Alice has to Bob, so that the Bob has the state of qubit bit 0 after some transformations on this his second qubit. So let's also go step by step with this algorithm and calculate how to obtain a state of this system. So suppose now that we have, let's maybe review some of the key steps in this protocol. So now we prepare the state Q0 we want to send to another qubit or another person, to Bob. Then we entangle 2 qubits, so Q1 and Q0. And after this, the qubit 2 can be separated to very long distance, no matter how far. Then we sort of create a inverse entanglement. There's not necessarily any name to this, but you can think of it as maybe the inverse entanglement or something like that. That will affect the state of both qubits. Then we measure both qubits, and depending on the measurement, we apply another set of gates to our second qubit to come back with the original state Q0. Okay, so let me begin with the state 0, 1, 0, 0. And here also the first qubit is shown as here. So after this X gate, the first qubit becomes 1. And now we apply Hadamard gate to the second qubit, which is now 1 over square root of 2, 1, 0, 0, plus 1 over square root of 2, 1, 1, 0. I'll open my notes regarding this quantum teleportation. After that, we apply a CNOT gate with the first qubit as the control and the second qubit as the target qubit. So after that, we have 1 over square root of 2, 1, 0, 0, plus 1 over square root of 2, 1, 1. Yes, because now the control qubit is 1, so we apply the X operator to the third qubit. I missed one here. Okay. So now we will apply a C naught on the first qubit as a target and the second qubit as the control. So after that, we are left with the state 1, 1, 0. And then actually it will be easier for us to, okay, let's leave it here and start it once again, because I will want to derive more general approach. So we can have any qubit. So this Q0 can be in any state A0 plus B1. Okay, this is state of our qubit 0. This can be any numbers as long as A squared plus B squared equal to 1. I'm sorry for this calculation here. It is relevant. However, I want the calculations to be more general and apply to any qubit of state 0 you would like to think of. But the application of those gates are still relevant. So let's begin once again with the state 0, 0, 0 plus B 1, 0, 0. Okay, so now this A's and B's corresponds to the entanglement of the values and amplitudes of the first qubit. So then we apply a Hadamard operator and entangle those two qubits. So after the entanglement, we know that we will get the states 0. We'll actually get 4 states. So maybe it'll be easier to write it step by step. So we have A 0, 0, 0. And here is 1 over square root of 2. Plus A 1 over square root of 2. 0, 1, 0. Plus plus B 1 1 over square root of 2. 1, 0, 0. Minus no, actually it's plus B 1 over square root of 2. 1, 1, 1. So applying a Hadamard gate on the second qubit here, and here is not entanglement, but just Hadamard, simple Hadamard. On the, first qubit in the notation of the Qiskit. So this is Q0, Q0, Q1, and Q2. And we apply a Hadamard gate here and here. And as a result of this Hadamard, we get 4 different states, each with different amplitudes, right? So Hadamard gates affects this qubit, this qubit, this qubit, this qubit, and this qubit. Then we apply a control NOT operator, C NOT, to every state of the. So let's review the states once again. In this case, the first qubit, this is the first qubit, this is the 0th qubit. This first qubit is a control qubit, and the second qubit, so this is also control, and this is the target. So this state does not change. This state will change to this state will change to 0, 1, 1 after the C naught. This state will stay the same, and this state will change to 1, 1, 0. So let's rewrite this once again. A 1 over square root of 2, 0, 0, 0, plus a 1 over square root of 2, 0, 1, 1, plus b 1 over square root of 2, 1, 0, 0, plus b 1 over square root of 2, 1, 1, 1. Okay. And I'm sorry, not 1, 1, 1, but 1, 1, 0. 1, 1, 0. This in the same order. So now let's apply the second control NOT. And now the first qubit is the control, the 0th qubit is the control, and the first qubit is the target. So after the applying of C naught, this state will be staying the same, will stay the same. 0, 0, 0. This will change to, this will also stay the same. But this here will change to 1, 1, 0. And this here will change to 1, 0, 1. Because we apply, in this case, we apply an X gate to the first qubit, because this is the control qubit. So after the transformation, we are left with, maybe I'll try to copy this because it may be faster. Rather than rewriting all the expression. Okay, so let's remark the states of the qubit as we said earlier. So this is actually stays the same. But now these states are different. This is changed, and this one is also changed. But I think I'm somewhere wrong here. This is actually 1, 1. Need to look at my notes. This is 1, 1. So this is after the C note. This is I was wrong here. No. 0, 0 is okay. But this is 0 here. Right? So this changes to 1, 0, 0. And I must have made a mistake in my notes. But let's move on. So let me review this once again. So the first qubit is the control and the second is the target. So control target, this is 0, this is 1. So the control is 1, it gets to 1, 1. Okay, this is 1, 1, 0. And then 1, 1, 0, okay. And this is 1, so this should be 0, 0. Okay, that should be fine. So now we apply a Hadamard gate to the to our first qubit. And now we will get a lot of expressions because this will be split to 2 expressions. This will also be split to 2 expressions. And we will, in fact, have 8 different expressions. So this calculations will be really long and really tedious to do. But now after the applying the Hadamard gate to every qubit, we will get, now instead of the 1 over square root of 2, you get 1 over 2. 0, 0, 0, plus 1 over 2, a 1, 0, 0, plus 1 over 2, a 1, 1, 1. I'm sorry, it will be 0, 1, 1, plus 1 over 2, a 1, 1, 1. That's okay. Plus 1, 1, 0, 0, 1, 1, 1, 0, 1, 1. That's okay. That's fine. Now we'll get to a different line, plus b 1 over 2. And this b, here we have minus. So after the Hadamard, we will have plus b 0, 1, 0, minus 1 over 2, b 1, 1, 0. And then the last b, the Hadamard on the last b, will be 1 over 2 b, 1 over 2 b, and now 0, 0, 0. And actually, this here shall be 0, 0. So I will review my steps somewhere because here should be also 0. Here should be 1. And if here is 1, then here should also be 1. I mean, I had to made some mistake along the lines, but this should be correct right now. So we have now b 1 over 2 and 1 over 2, but minus because of the Hadamard applying here. Apply here. 1, sorry, yes, 1. No, it's a 1, 1, 1. I'm sorry, 1, 0, 1. No, 1, 0. 101, stuff like that. It's a lot of yes, because here yeah, we now write this term here. So it's 0, 0, 1 and 1, 0, 1. There are a lot of tedious calculations and it's very easy to get stuck. So I'm really sorry for that. But now we will try to group all of those bits and pieces together. And I will now color all of the A and B's that have 0 and 0 as the first qubit. So here we have 0, 0. And we will match this with the term 0, 0 here. Okay. Now let's match the term 0, 1, 0 with another term with 1, 0. Let's match the term 0, 1 somewhere. 0, 1 is here. And 1, 1. 1, 1 was somewhere here. Yes, exactly. So now we'll group each of the states as we'll take the 1/2 in front of the bracket and write very big parentheses, something like 0, 0, A, 0 from this expression here, plus B1 from this expression here, plus, and this is close the parenthesis, plus, maybe I'll try to do it line by line. With, now we go with 0, 1. And the 0, 1 is labeled as right here. So actually we have A, 1 plus B, 0. Okay, so B0 goes here and A1 goes here. Now let's write 1, 0, which shall be A 0 minus B1. And you will confirm that from this graph here. And minus, it shall be, yes, here shall be minus, not plus, minus B1 from here. And our, this is also a cat. Don't forget, we shouldn't forget about it. Or we could just drop it. It's only a notation thing. And the last is 1, 1, which is a 1 minus B0. Now you can see, and close the parentheses. Now we will see that I will only draw the lines here. The last lines that are left are here. And now you are able to measure, based on those 2 qubits, the measurement of those 2 qubits, you have to apply different gates. So in the first case, you just do nothing. And the third qubit is the state A0 plus B1, which we begin with. In this case, you have to, if the outcome of the measurement is 0, 1, you have to apply an X gate. So after applying the X gate, the state of the qubit will be A0 plus B1. In this case, when the measurement of the 0th and first qubit is 1, 0, you apply only the Z gate. So the phase will be back to the state A0 plus B1. And in the last case, when you measure 1, 1, you apply both X and Z gates to obtain also a state plus B1. These were very long calculations, but I hope you get the idea. There's a question in the chat. Can you explain the first step, the X gate, X1 gate? So actually, the first here is the preparation of our qubit. And for the purpose of this particular circuit, I chose this state to be 1, to teleport the state 1. But here we derived a protocol that you can actually teleport any chosen state A0 plus B1. The last term should be 0, 1, 0, 0. It should not. But why is that? It's invalid question anymore. Okay, sorry. So yeah, now you can see that this protocol works, and it requires only few gates to be implemented. And actually here you have control, but you can also send the information classically through some communication channels to apply either both or both gates or either one of them. Yeah, so that's how the quantum teleportation works. Do you have any questions to this?
Maybe can you comment on the, can you show the graph?
Yes.
And how you have here those two measurements, yes? And
Yes.
after that, you have this blue things, yes? And
Yes. The
how
control
do they
Z.
Yes, this is control. No, this is controls. How
This
this
is
is
control X,
yes.
and this is control Z. So the matrix of the control Z, control Z gate, let's say, is
Okay.
1, 1, 1, minus 1, and 0 elsewhere. And what this gate does is the state 0, 0 stays the same. Likewise, the state 0, 1 also stays the same because the control qubit is 0. 0, 1. But when the control qubit is 1, the phase of so actually it's not like that. The phase of the second qubit is changed, so it's, or in fact both of the qubits. That's why you don't really need to write which one is control, which one is not. The phase here is reversed. And this happens also to the, sorry, not minus here, to the state 1, 1. So both minuses should be here.
Because on this graph I'm a bit misled because the icon here is the same as for C naught.
Not really, because the C naught has like some plus here, and the control Z does not have this plus, and that's why.
Okay. So, but the first one is C naught, yes.
Yes, and the second is control Z. I mean, in this particular case, the order of those operations does not matter. because these are now like after the measurement, the qubits become like classical bits. So these are after those measurements, these are now classical bits of information. So
Okay.
if you are in this particular example, it doesn't matter whether you apply to in the last case, whether you apply X gate first or Z gate first, or in reverse, because the output will be the same. But in
But
general,
okay,
this is not true.
okay. You have here XZ, yes, and here you say CZ.
Control Z.
Control
Right.
Z, yes. And is this the same as the one at the bottom, like the superposition of X and Z?
This one, yes. I mean, it's not the same. It's like two gates applied in
Yes.
in order. But what you see here is that, in fact, it is sort of a control Z, because here you see that the first bit, if the first bit is 00, it corresponds to well, maybe I may have somewhere reversed the order here, but actually you should be able to see that in some cases uh, the Z in those two cases the Z operator is applied, right? So these two bits correspond to applying the Z operator. Yes, now I'm back on track, let's say. And the second bit tells you whether to apply an X gate or not. So in these both scenarios, the first bit is 1, so you have to apply the Z gate. And this is exactly what we can see here also, right? If
Okay.
the 0 of qubit is in state 1, then we should apply the Z gate. And in this, once again, I must stress it that in this particular example, the order of those gates does not matter, but it's only this particular algorithm.
Okay, thank you very much.
Yeah, so once again, depending on the measurement of the first and second qubit, we apply different combination of X and Y gates, but we can also call them control gates, because you can see that the Z gate is activated when the first bit is 0 bit is 1, and here the X gate is activated when the second bit is 1. Okay, now the last topic I want to cover is the multiple control sequence. Control operators, constructors. Yes, multiple control constructions, and now we ask the question how to control a gate, because we had a CNOT gate, which was affected only when the first bit was 1, right? But now we want to create a gate that will be affected when the first bit is 0. So we can also call it C1, not because this has effect only when the first bit is 1. So as we said earlier, this is 0, 1, this is 1, 1, and this is 1, 0. So now we want to construct a C0 gate that will be activated only when the first bit is 0. So we apply a NOT operator on the second bit when the first bit is 0. The question is how to do that. Am I right? No, I'm not. This is 0, 0. 1, 0. And once again, this is now not affected. The second bit is not affected. And in this case scenario, the second bit is also not affected. It turns out that in order to construct this operator from standard quantum gates, you need to apply an X gate before the control Z. So actually the circuit of such a C0 naught will look like this. So in this case, we apply a, let's say, C1 naught gate only, but first we change the value of the first qubit. This is also now reverse computation. So here is Q0 and here is Q1. Okay, so and we also apply another X gate after the control to revert the qubit 0 to the original state. And actually, the matrix representation of such a C0 naught will be 0, 1, 1, 0. Here we have all zeros, and 1, 1 on the diagonal. This will be the matrix representation of such a gate. Yes, because now you can see that those two states are like interchanging, and that's why we see those ones on the off diagonal. But let's ask a question if it is possible to construct a C naught gate. This gate actually can be implemented on a quantum computer, and it is now a 3 by 3. No, it's not. It's 4 by. This is 4 by 4. So 3 will be 8 by 8 matrix. Because this is 2 to the power of 3 qubits times 2 to the power of 3 qubits, which is 8 by 8 matrix. So I will not write this, but the idea is that if both qubits are 0, no matter how what is the value of this one, of the third qubit, the maybe not X is not good, will be some, for example, A. Then the result will not change. And the same is true for any other combination of zeros and ones, but with the exception of when both qubits are in state 1, 1. Then we apply, only then we apply a X gate. So we have now X as a NOT operator that's acting on, you can also add a little hat on letter to indicate that this is a matrix and an X operator on the third qubit. But you can also ask a question how to construct a C1, so this is C0, C0 naught. So they're both, no, I'm sorry. They're both C1, C1 naught. So they work only when both qubits are in one state. But you can also try to construct the different combinations of those gates. And this is what the last notebook is about. Constructing the different combination of C0 and C1 NOT gates. And I will not cover this because we don't have much time. This lecture is already very long, but this is the last notebook. This is the question of the last notebooks you will consider. But, and this is also called Toffoli gate. Toffoli gate. But you can also ask a question, what to do with multiple control C naught. And it turns out that it's not possible for a quantum computer to implement such a gate. We can also take use of the Toffoli gate. And therefore, in order to construct such a system that's based on the 4 qubits, we will take advantage of another qubit, which we'll call auxiliary qubit. And this is our, let's say, Q, this one. I don't think it does matter. Let's say Q0, Q1, Q1, Q2, and Q3. So we will map the C naught, C naught. We will map the state of those two. I'm sorry. Here we have 3 qubits. Okay, so let's once again write the circuit representation of this Toffoli gate. So we will have 2 control qubits, and so we have Q0, Q1, and Q2. And only when the first 2 bits are 1, then we'll apply the NOT operator on the Q2. But now we have, instead of 2 qubits, we have 3 qubits. So we'll take advantage of the auxiliary qubit. So first we take 2 qubits, state of 2 qubits, and we map the state of those 2 qubits to an auxiliary qubit. And this auxiliary qubit will only change its state whether both Q0 and Q1 are in state 1. And in other case, this won't happen. So now we have the information about these 2 qubits in our auxiliary qubit. So we can take advantage of it and write a circuit, I'm sorry, not here, but here. Now we can implement under C0 gate. And therefore, by using the auxiliary qubit, we can access the information of Q0 and Q1. And then we will also apply another CC0 gate to revert the auxiliary qubit back to the original state. So after applying those 2 gates, we will make sure that auxiliary qubit goes back to its initial state. So yeah, in the notebooks, you will also try to implement CCCC gate. And this is exactly the same. You just need 2 auxiliary qubits and map the 3 states, actually 4 states of 2 qubits to those 2 auxiliary qubits, and then you will be able to implement a control X gate to the last qubits. Okay, do you have any questions to this last topic? How do we know for 0, 1x gate is applied and for 1, 0x is this is back to the teleportation question. So I will answer it in a second if there are no other questions. What is the use and difference between entangled qubit and teleported qubit? Okay, there's a discussion in the chat. Okay. Do you have any questions? I can see that thank you, Przemek, for answering the questions in the chat. Do you have any more? So if not, then thank you for attending today's lecture, and I wish you good luck with the notebooks. I think they are more difficult than the notebooks yesterday, but I hope you will manage. And if you have any questions, you can always write to us on Discord, and we will be available and to answer your questions by the 9 o'clock CTC. So we will be on the Discord for 1.5 hours. And if you have any questions, you can also hop to the voice channel, and I will try to sit there and answer your questions if you have any. And other than that, I would like to thank you for today's lecture, and see you tomorrow. Goodbye.